Okay. Okay, so what we want to do, what I was saying here, everyone, is we want to expand. So in elementary school, when you talk about solids, liquids, and gases, you take it a lot from the standpoint of what we actually see with our eyes, right? This is a solid, this is a liquid, that's a gas. What we want to do is take that knowledge and expand it down to the chemistry level of what we're not seeing, right? What are the molecules in the solid and liquid and gas doing, right? So first off, on your notes, label for me solid, liquid, gas. I think we're okay to not write down the properties because I think, once again, we're familiar with them, right? That solids are packed close together. Are solid molecules moving?
Yes.
Yes. Right? Lots of times they say it's a vibration, right? But they are moving. Liquids are moving more, and then gases are moving the most. Okay. With this idea of solids, liquids to gases, what makes the difference? Like, water is still water. It's still H2O in all three phases. So what makes something a solid versus a liquid versus a gas at the chemical level is it goes down to those intermolecular forces. Those attractive forces that we've been talking about is what holds it together. If things didn't have intermolecular forces, everything would be a gas. Because why would they stay together if there was nothing holding them there? Okay? So then, the next question that we're going to talk a lot about today is how do I overcome these attractive forces? So if I want to change something from a solid to a liquid or to a gas, what do I have to do to overcome the magnets?
Add energy.
Add some sort of energy. Typically we say it's heat, right, to the particles. By adding energy, I can pull the magnets apart, changing their phases. Okay? So with this idea of our three states of matter, something I want you to change in your mind is what we define temperature as. Okay? When you go and you check your phone and you ask somebody, you say, hey, what's the temperature going to be outside? Typically you're asking that question because you're wanting to know if it's hot or if it's cold, right? What we want to do is change our definition of temperature to what it is chemically, actually. What temperature is temperature is a measure of motion. It's a measure of how quickly or how slowly the particles are moving. Hot and cold are simply what we use to describe it. But when it comes down to it, something that has a high kinetic energy is at a higher temperature. Okay, so temperature is actually simply a measurement of movement. And I'll do a little demo for you next time that will hopefully help them. Okay, so with this idea, right, so you can look at it as when I go from a solid to a liquid to a gas, the temperature is increasing, the motions are increasing, but our interactions are actually decreasing. Gases do not experience attraction to each other, hence why they're far apart. We're going to look at three types of graphs today, and you want to be able to interpret what they're saying and label their different parts. Okay? So this is known as a heating curve. Any heating curve is a measure, so write in these on your axes, is a measure of temperature versus the energy added. Okay, temperature versus energy added. So what's going on in this graph is, particularly this is a one for water, but all of them would have a similar shape to them. So imagine here for you, sorry I didn't do this for you in real life, but I think we've all seen water boil. I didn't think I needed to do it as a demo. Okay, but let's say I have up here a beaker that is just solid ice. Okay, so the first part of my graph represents when our substance is a solid. Okay, while it's a solid, I can heat that solid and get the solid hotter and hotter and hotter. Once it gets to its melting point, the temperature actually no longer changes. So this part of our graph is the process of when it begins to melt. So as our ice is melting, that means we have both solid and liquid in existence, and the temperature doesn't change. You could easily test this at home with just a thermometer, and if you just leave the thermometer in it, you'll see that it will stay constant until all of the ice is gone, and it's all then just a liquid. Once it's a liquid, I can then heat the water, make the liquid hotter, hotter, and hotter, and hotter until, what would be the next change? Yeah, so then when it starts to boil, once again, the temperature stays constant. While water is boiling, your temperature doesn't get any hotter. It stays the same.
Wait, so question. So
yeah.
if I have like, you know, a cup of water or whatever, and I have like just a piece of ice in it, so like I can heat and cool this the water, but the water itself won't change until the ice is gone.
While you get like an equilibrium state, yeah, and that liquid will not increase in temperature because all of the energy is going into pulling apart the magnets rather than into making them move faster.
Okay.
Does that make sense? Yeah, so interesting idea. And then, so right here, when it's boiling, what are the two phases that are both in existence?
Liquid and gas.
Gas and a liquid, right? And it's not going to get any hotter until it all changes to a vapor or gas. And then if I had it contained, I could heat the gas and make that hotter. Right? You can also look at this graph in reverse. So if I had a gas, what's the phase change to go from a gas to a liquid?
Condensation.
Condensation. So you can also consider this as a point where it's condensing. Right, if we're going backwards. And then what's the opposite of melting? Solidifying or freezing. Right, so we can look at it in that direction as well. Another way we can say these things is this first plateau we often will call the heat of fusion. Okay, and the symbol for it is delta H of fusion. Because what does the delta mean again? Change in heat of fusion. Yeah. Be careful with this one because we've talked about fusion before, but it meant something very different. What did fusion mean in our nuclear chapters? Yeah, that was when atoms collide and make a bigger atom, right? In phase changes, fusion is actually a word for melting. So just be careful with that. And then our other one up here, this one is known as the heat of vaporization.
It's a cool word.
Yeah. It's delta H of vaporization. You can abbreviate it if you want to. Okay, so what these are describing is this describes how much heat it takes to change something into a vapor. This is how much heat it takes to melt something. Okay? All right, another thing on this graph that we want to pay attention to here is the difference between kinetic versus potential energy. So what did we say temperature is a measure of? Kinetic energy. So if my graph on the y-axis is flat, at this point in time, is my kinetic energy changing? No, right? So what happens in a cup of water is that while the ice is solid, the kinetic energy is increasing, right? So this is a kinetic change. But right here, it's now a potential energy change. All the energy is going into breaking the intermolecular forces. So this would be potential. So then now that it's all liquid, what type of change would this be?
Kinetic.
Kinetic, yep. So anytime the graph is, in a sense, slanted, it's a kinetic change. But then when it goes flat, it goes back to potential. Yep, so this would be potential, and then back to kinetic. Okay? So if you look underneath the graph, there's just a few key bullet points of your notes. Okay? So the first one, fusion, means melting. When we talk about phase changes, so that's just maybe a different way of thinking about it. And then another key thing to pay attention to is with it is that kinetic energy does not change during a phase change. Right? The phase changes are when the graph is flat, and kinetic energy is constant, because kinetic energy is temperature. Right? Those two things are interchangeable. all the energy is stored as potential. And then we often call this energy as latent heat. Latent meaning hidden. Because heat is going into the cup, but you don't see the heat making it hotter and hotter and hotter. And so that's why it's called the hidden heat. Okay? All right, for some smiley faces, grab your periodic table in front of you. Okay? We're going to say A is true and B is false. Okay? So based on what we just talked about, tell me here, true or false, does kinetic energy increase as ice melts? A is true, B is false. So show me your answer. Good. Why is it false? During a phase change, kinetic energy is constant, right? If you look on your graph, where's melting happening? It's flat, right? So it's based off potential. Okay? So then, number 7, answer this one. Potential energy increases as liquid water gets warmer. So if you want, look on your graph. Look at where liquid water is getting warmer. And is that kinetic or potential? True or false? Good. It is also false because where is the liquid part of your graph, slanted or straight? Slanted, which means it's not potential, it's kinetic, right? Because it's one or the other here. So then number 8, potential energy increases as water boils. True or false? Show me your answer. So look at where water is boiling. Is it potential or is it kinetic? Good, everyone, it is potential. Good, so it is true. Have a smiley face for each of those that you got correct. Okay, so once again, as we look at these phase changes, it goes back to the idea of attractive forces, okay? So the melting point is simply the point when something changes from a solid to a liquid. In order for this to happen, we have to have it where the energy equals the attractive forces. You have to have enough energy to bring those molecules apart from each other, otherwise it won't melt. So tell me this, if something has a really, really high melting point, does that mean it has strong or weak forces?
Strong.
Yeah, that means it's going to be really strong because it needs a lot of energy to pull it apart. Right? Things that melt quite easily, we'd consider their forces to be weaker. Okay? The other phase change that we want to talk about as well is boiling. But our idea of boiling, I also want you to shift a little bit. Okay? So boiling by definition is simply the process of changing something from a liquid to a gas. Yeah?
Is it also opposite? So if strong bonds means harder to boil, does it make it easier to freeze?
Yeah. Right, because they already want to come together, so it's going to freeze really easily. Yeah. No, that's a great comparison. So with this idea of boiling, here's what I want you to shift though, okay? In order for something to boil, the water needs enough energy to break out of those attractive forces. But it also has to overcome the pressure pushing down on it. Okay? So here's kind of a way that somebody once told me, I think is a really great way of thinking about atmospheric pressure. Okay? If somebody once said that we live in an ocean of air. Okay? So imagine this with me, right? So you can feel the ocean around you by doing this. Ready? Everyone take your hands like this. We're all going to look silly, but it's fine because we'll all do it together. And you're going to wave your hands back and forth. And you can feel the ocean. Do you feel it?
Oh my gosh.
Right? It's there?
I feel wet.
Yeah? Right? It's not like a pool where you can feel it a lot. But if you move your hand, you can feel the pressure that's around you. Okay? So on the earth, we live in an ocean of air, right? So don't worry about this, I'll come back, but I wanted to show you a picture that's farther ahead that helps visualize this. Okay? So these little blue dots are, in a sense, air molecules. Okay? So the closer we are to sea level, the deeper we are in our ocean of air. Right? And the higher up in elevation you go, that's why the air is getting thinner, is because you're nearing the top of the ocean. There's less pressure at the top than there is at the bottom, right? Which is why, like in normal water, if you jump into a deep pool and you go really deep, right, your ears pop. You can feel the pressure. For us, as you go higher and higher, there's less oxygen to breathe because you're nearing the top of the ocean. Okay? So when something boils, it not only has to overcome the attractive forces, but it has to have enough force to push out of the pressure pushing down on it. Okay? And this is connected to what we call vapor pressure. Whoa. What's going on? So in order for something to boil, the vapor pressure has to equal the atmospheric pressure. Okay? So this right here is known as a vapor pressure diagram or graph, and it can show us at particular pressures what something boils at. Okay? So the vapor pressure is the pressure exerted by gas molecules of a specific substance. Okay? So in a sense, boiling point is the temperature where vapor pressure equals the atmospheric pressure. So when those two things are equal, then something will boil. So here's kind of a shift of boiling, okay? So think about this, ready? Do we have more or less pressure here in Utah than in California?
More.
Less. So we're at a higher elevation, we're higher in the ocean, so we have less pressure pushing down on us than they do in California. So would that mean, does our water boil at a higher or lower temperature? Is it going to be easier to boil here or there? Easier, because there's less pressure pushing down. Our water boils at about 95 degrees Celsius instead of the standard 100.
So is the 100 at sea level?
100 is based off, at sea level. But then, here's an interesting thought. So just because our water is boiling at 95 degrees, is our food going to cook any faster? No, because 95 degrees is still 95 degrees. If you go on the top of Mount Everest, water boils at 70 degrees. But is 70-degree water going to cook your pasta very well?
Heck no.
No, right? You actually can, one day I hope to have these, but if you have a vacuum chamber, you can get water to boil at room temperature. The beaker of water will be boiling and you can stick your hand straight in it. And you're not getting burned.
That's so weird.
But is my boiling water going to cook my pasta?
No.
No, because it's tap water. Tap water, you're just getting your noodles wet.
So like you
What would
could
it
make
be like-
pasta on Mount Everest.
No, not very well, right? Take up probably a really
My
long
last
time.
dream is over.
Yeah, it's kind of just a different way to think about boiling, right? Because boiling we normally think of as hot, but it's really not. It's just about having enough energy to overcome the pressure around it, right? So when we read this graph, okay, so let's say we wanted to find the boiling point temperature of chloroform. We're going to say we're at sea level. So here's standard pressure. So standard pressure is 1 atm or 103 kilopascals or 760 milligrams of mercury. So these are just different units of pressure. Like in temperature, we have Kelvin, Celsius, and Fahrenheit. Those are just the different units. So with your pencil, what we're going to do is, since we're saying we're standard, we're looking for chloroform. So start by going up to the top where there's that line of 101.3 and draw a straight line across, so it's dashed in blue now. So draw a line over to chloroform because that matches up our pressure, and then draw a line down to temperature. And there's our answer. So at standard pressure, chloroform will boil at 60 degrees. Okay? So try that same thing and do it for ethanol. Was that the one I put underneath it? Is another problem? So try to find what is the boiling point of ethanol now at standard temperature. Standard pressure. When you have an answer, put your pencil down. Okay, and then on the count of 3, you're just going to shout it out loud. Ready? 1, 2, 3.
79.
Good. Yeah, about 78, 79. Follow the line down somewhere in that range. Okay? Questions on interpreting a vapor pressure graph? Yeah, Maddie.
So at 100 is the standard point, is that what you
101.3 is standard. Yeah. So then for us, okay, so since we're not at sea level, we're at a higher altitude. That's why they often say the air is thinner, because it literally is. Okay, we have a lower air pressure pushing down on us. Our air pressure is we sit at about 84.2 kilopascals. So if you look on the vapor pressure graph above, instead of being at 101, the standard, we're at 84.2, which when you carry that across and down, it changes the boiling point. Yeah.